you're not imagining things. When I went to upload my videos, I had lost this problem that's missing at the top. So I just erased. I'm going to re-record it. The problems below are on another video. So I just had to come in and erase this section and start over. So you are not imagining things. I'm looking at page 161 in the book, the textbook, and this is that margin problem. It's called the Core Practice Model with Mathematics. It says the graph shows the estimated resting heart rate in beats per minute based on a person's age. Now, if you have the textbook, you already see the graph, but I'm going to draw the graph for those who may not have the book. I'll also want to tell you about it as I draw it. Okay, in this graph, the independent variable is age in years. And we have an age from 0, 2, 4, 6, 8, 10. So up to 10 years old, we have a marker, a label. We could plug in these missing values. They've just left out the odd numbered years for easier to read graphs. But it is scaled in single years. Each line over is 1 year older. Okay, then we have the dependent variable, which is resting heart rate. And we have a squiggly thing right here. And then it starts off with 85, 90, 95, 100, 105. So this axis is scaled by 5. So every 2 boxes represents 5 beats per minute in the resting heart rate. Okay, let me just pause a second. I want to put a thought into your mind. If you've ever had a fetal ultrasound, or if you've ever performed a fetal ultrasound, or seen one, you may have thought that a baby that is still in utero has a very high heart rate. It can be alarming if you don't know what's going on. I believe it's about 150 for a child in utero. It's a lot higher than my heart rate. If my heart rate goes to 150, I go to the hospital. Or I could go to the hospital. Now, if I'm exercising or something, that's different. But a resting heart rate for a neonate, a newborn, is pretty high. So as I graph this, I want you to keep that in the back of your mind. That's a practical experience that a lot of people have had, is being at the doctor's office and having that ultrasound done. They give me a point in the book on their graph that says that at 4 years old, the resting heart rate is about 100. This is for an average healthy individual. At 10 years old, the resting heart rate is 85. So when you're 10 years old, you can expect to have 85 beats per minute at rest. So this graph is showing me a very important, I didn't graph that correctly. Did you catch it? I put it over on the 11-year-old line, which is not going to work. So it's 10 years old, 85 beats per minute. When I graph this thing, it is confirming something for me. And this goes back to that example of the newborn in utero baby, or a brand new baby that's just been born. Okay, I have to get this right, or I can't show you some things that I need to show you. Oh, goodness, guys. It's time to stop for the day. That's close enough. It's close as I can get it. My graph is not perfectly square, and that's the problem. It's just not going to be perfect. But this is showing me a very important scientific observation. As a person gets older, or as age increases, resting heart rate does what? What's the slope of this line showing? It decreases. It goes down. Okay? Now, it doesn't just plummet. It steps down at a predictable, consistent rate of change. Before we get to that, I want to call your attention to two things. The first is this squiggly thing. Let's figure out why that squiggly thing is there. Now, I know that this y-axis is scaled at 5, intervals of 5. So every 2 boxes on the y-axis is 5 beats per minute. Now, from 0 to 85 clearly is not 5 beats. That 2 boxes represents 85 beats per minute. So what that squiggly thing is showing you, it's calling your attention to the fact that the scale is not consistent. This is a very good thing. People who want to misrepresent data in graphs do not use squiggles. Because if you put the squiggly thing in there, a person's eye is going to go to that and they're going to ask what's going on there. It's calling attention to the fact that there's a jump in the scale. Why is there a jump in the scale? Why would we not start at 0 and do 5, 10, 15, 20, 25, 30? For one thing, if your heart rate is 5 beats per minute at rest, you have a more serious problem than this graph. You are nearing death at that rate. So that is not a relevant heart rate here. A 10-year-old with a heart rate of 5 is not a healthy individual. So that's one reason. You don't need to show heart rates that low because they're not relevant. The other thing is that the graph would be so big, it would be hard to fit on a page. So they have just shown you the graph for the data that they needed to show you. They're not showing you every single point from 0 to 105. The other thing I would like to call your attention to, now the graph in the book doesn't show this, but I really want to know the y-intercept, at least to have an idea of the y-intercept. Where does that line cross the y-axis? Well, if we graph that point, you can see that it's at 110. Now, if I needed to use this number in a formula, I would not guess. I would work it out. But the y-intercept, let's just review what that is. It is the point where the line touches the y-axis, and it is a point. The x will always be 0. And the y is that b value, the baby b, that we've been looking at all through this course. That is the point, and I believe it's about 110. I actually know it is because I did the formula in another thing, and it is at 110. So that is where, at 110 beats per minute, is where the y-intercept lies on this graph. And that would correspond to a newborn, a baby that has just been born, 0 years old. You could expect about 110 beats per minute. It's higher than that in utero. I actually think it's higher than that for an infant. Let me Let me just Google that on another screen. What is the resting heart rate of a newborn? A baby that has literally just been born. Well, it's 110 to 150 beats per minute. So I guess that is pretty accurate, right in that range. In utero, I would expect about 100 up to 150 beats per minute. Okay, so as the person gets older, the resting heart rate decreases. Let's build some stairs. I'm going to pick a point. I'm actually going to start up here at 110. And I know that for every 2 years, there is a 5-degree, in this case, drop. Actually, let's back up. Let's start down here. At 10 years old, your heart rate is 85. Okay, if I go back up through my life history, I go 2 boxes, and remember that represents 5 beats. Because from 85 to 90 is 5 beats. And it runs 2. That represents 2 years of life. And then I back up again, 5 beats. In 2 years. 5 beats in 2 years. 5 beats in 2 years. And we already built that step. So look at these stairs. Think with me. What is happening as I get older? My heart rate is doing what? Is it plummeting? Is it going up and down? It's stepping down at a consistent, predictable rate. And I want to call your attention to the fact that this is a function. That's the definition of a function. That it is changing at a predictable, consistent rate. So would you agree that in this form, we drop 5 beats every 2 years of life? That's what this graph is ultimately telling us. Sure, it's changing over time, but how is it changing? That's the question we're looking at. How is it changing over time? What is that pattern over time? And it is negative 5 beats, drop 5 beats every 2 years. Okay, our first instruction is to use this information to write an equation of the given line. So if I knew slope, I could write this equation in point-slope form because I have a point, I have 2 points, and if I just knew slope, I could do that. So let's find slope. Say it with me. Slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And let's look at these points. I'm going to let this be x1 and this be y1, x2 and y2. So I will say 85 minus 100 over 10 minus 4. So I get negative 15. I like that because my staircase is going down, over 6. So slope is negative 15 over 6. That can be simplified a little bit by 3. 3 into 15 is 5. It would be negative. 3 into 6, this is my reduction factor. 3 into 6 is 2. So slope is negative 5 halves. Where have you seen that before lately? Did I have to do the slope formula? No. I could have taken my slope from this. This is the same thing as that formula. That's the reasoning behind that formula. That formula represents this staircase. Okay, now that we are sure of slope, let's use point slope to answer the second part of our question. Well, I haven't answered the first part yet. It said to write an equation for the line. So I'm going to use point slope form. And let's get our thing going here. So we have to recall the point slope pattern. Now I know slope is right up there. The point I'm going to use is the 4/100. You can use 1085 if you want to. It doesn't matter. The point slope pattern, say it with me, is y minus y1 equals m x minus x1 in parentheses. And we just found slope. That's negative 5 halves. Let me color code for you. There's slope. That's m. X stays in the problem, but we know x sub 1 is going to be this 4. And then we can do the other side. Y stays in the problem, and y1 is 100. And I'll color code that for you. There's the 100 that goes right here. So we used a point and we used slope, and we need to simplify here. Y minus 100 is simplified. Nothing I can do there. Negative 5 halves times x. Negative 5 times negative 4 is positive 20. And don't lose your 2. So I have y minus 100 equals negative 5 halves x plus 2 into 20 is 10. So there's the equation in point slope form. Well, it's almost. I need to put the equal sign back in there, because if you have an equation, you must have an equal sign. It didn't specify what kind of equation. It didn't say standard or slope-intercept, so I'm going to leave it right there. I have written an equation like they said to do. And then it says to use that equation to find the resting heart rate of a person who is 20 years old. So when age is 20, what would we have? Well, we would have y minus 100 equals negative 5 halves times 20 plus 10. So I would have y minus 100 equals negative 100 over 2 plus 10. Y minus 100 equals negative 50 plus 10. Y minus 100 equals negative 40. And then let's move the 100 because we want y by itself. We know x, we need y by itself. So you would be saying this cancels. Y is 60. That is the heart rate for a person who is 20 years old. You could also write it this way. When you're 20 years old, your resting heart rate is 60. I bet I have some nursing students in this course, future nurses. May even have some future doctors in this course. I had a student years ago who is now a top-notch surgeon. So I've learned to never underestimate the power of education. If you are a nursing student or about to be a nursing student, this would make a wonderful project. If you have to do a capstone project or a senior project, this would be a great way to do it. You could gather up some people, take their heart rates while they're resting, and do this math as your project. I would love to do that. If you need help doing that, let me know. I would be glad to help you set that experiment up. All right, guys, this brings us to the end of this problem, and I will see you in the next video for, I'm assuming, this problem that I've already done. So have a great day, and thanks for joining me.